Welcome to a short PRACE video training on OpenMP synchronization constructs. We will start our training with a simple example to illustrate the need for synchronization constructs and then move on to more advanced examples on how these constructs are implemented in real-world cases. In our examples we will use the GCC C++ compiler. Some introductory level acquaintance with compiling from the command line is needed. OpenMP is a shared memory parallel library. Thus, in essence, all variables defined in an OpenMP region are shared among the parallel threads unless otherwise noted. Look at this example code. The parallel region is to be executed by two threads simultaneously and x is a shared variable. As x is shared, it will be incremented twice, once by one thread, the second time by another thread. But there is no way of knowing beforehand which thread will step in first and which second, and which thread will reach first to the point the x variable is called in the printf statement. To illustrate this, we will compile now the code and see what happens when we consecutively call the execution of the executable. Note that in order to compile the code, we are using the -f OpenMP flag. The name of the flag depends on the compiler we are using, so if you are using something other from GCC, please refer to the man page of your compiler to find the corresponding flag you should be using. Once the compilation is done, we may execute the executable file several times, and what we can see is that x is being incremented twice, each time by one thread. The order of incrementation cannot be known beforehand and changes time after time. To remedy a situation like this, some sort of synchronization must be implemented within the OpenMP parallel region. Something to tell the threads which should do the incrementation first, then second, or just to synchronize the threads once the incrementation has taken place. First of all, let's start with discussing the barrier directive. The barrier directive can be used to synchronize all threads in a team of threads. When a barrier directive is reached, a thread will wait at that point until all other threads have reached that barrier. All threads then resume executing in parallel the code that follows the barrier. On top of our previous example, we shall now insert such a barrier directive before the printf command is issued. This way we can control beforehand that when the x variable is called from within the printf command, its value will be 3. In other words, x will have been incremented twice by the two threads. Note, however, that even though now we can be certain about the value of x after the incrementation, we still don't know which thread incremented x first, then second. One way to work around this problem is to use the Master Directive. The Master Directive specifies a region that is to be executed only by the master thread of the team. All other threads of the team will skip this section of code and move on. Note that there is no implied barrier associated with the Master Directive, thus a barrier should be explicitly set. Building on top of our base example, we now instruct within the OpenMP region that only the master thread will increment x. This means that x will now have the value of 2 when the printf statement is reached by the two threads, as x is now incremented only once by the master thread. We again compile the code and showcase what's taking place by executing the executable file. Another way to implement this sort of synchronization is to use the single directive. The single directive specifies that the enclosed code is to be executed by only one thread in the team. Which one we cannot know beforehand. Note that threads in the team that do not execute the single directive will wait at the end of the enclosed code block unless a no-wait clause is specified. Having said that, in the case we're using the single directive, there is no need to further use the barrier directive at the end of the single region, as synchronization will be implicitly taken care of. We can showcase this by going back to our original example and inserting a single directive on top of the incrementation process. As we are not using the no-wait clause, the threads will synchronize before they call the printf statement, thus the value of x will always be 2. Going now back to our first example, where x was incremented twice, we want to discuss how to better handle such a situation. A better gain control of what is going on in such a case is to use the Critical Directive. The Critical Directive specifies a region of code that must be executed by only one thread at a time. Thus, if a thread is currently executing inside a critical region and another thread reaches that critical region, and attempts to execute it, it will block until the first thread exits that critical region. This directive allows us to gain a better level of control of the incrementation procedure we have used in our first example. In addition to inserting the critical directive on top of the incrementation process, we need to also explicitly define a barrier statement, as there is no implicit synchronization induced by the use of the critical directive. As you can see in the output of the executable, the value of x in the printf statement now has always the value of 3. The difference from not just using the barrier directive is that in this case the incrementation is fulfilled in a thread-safe manner. This concludes our short introduction to OpenMP synchronization constructs. Thank you for watching.